This is a picture of Earth from moon. From moon. From the moon. Why am I including this picture? Well, one, it's often credited with kicking off the environmental movement on Earth, but also because it highlights the amount of water that exists on our home. Water is crucial to life. All life that we know of requires water. Why is that? Why is water so important? Well, let's take a look at water, and this will help you understand why. So here is a water molecule. It consists of an oxygen atom and two hydrogen atoms. These hydrogen atoms are covalently bonded, meaning they share electrons with oxygen, which means it's a very strong, tightly held bond. But that's not all that's happening here. Notice that these hydrogens are kind of pushed down to the side. They're not out horizontally to oxygen. They don't form a flat molecule. They form this bent or upside down Mickey Mouse shape as you're looking here. Why is that? Well, this has to do with some distinct chemical properties of oxygen. Oxygen is what we call very electronegative, meaning that it really pulls electrons towards its nucleus. It really wants electrons orbiting it. So whenever it binds covalently to hydrogen, these shared electrons are going to spend most of their time orbiting oxygen and less time orbiting hydrogen. Most of the time, once again, these electrons are orbiting oxygen. This results in a net negative charge. That's what this is saying right here. It's a partial negative charge. Partial negative on the oxygen and partial positive charges on the hydrogen. We call this a polar molecule. It's got two distinct poles. It's got a negative side and a positive side. What does this mean? Well, it means that water sticks to itself. It also sticks to lots of other things. But this stickiness is caused by a bond called a hydrogen bond. And this is a bond between two polar molecules. So the positive hydrogen here is going to bind to the slightly positive negative of this oxygen. Right? And so a single water molecule can bind to several different other water molecules. This is what creates water tension and why water will move up a straw without you even having to create a vacuum to move that liquid up it. So water is super important. The shape of water, literally, is one of the reasons why water is so important. That shape is obviously caused by the electronegativity of oxygen. A shortened version of electronegativity is affinity for paired electrons. Oxygen really wants to pull electrons toward it. Oxygen, not so much. This is going to result in that polar molecule I just mentioned, where you have a slight positive end and a slight negative end, which is going to form hydrogen bonds. So I mentioned that water doesn't only just stick to itself, it sticks to other things as well. Here is water binding to a couple of ions. Here we have an anion, chlorine. So slightly positive hydrogens on the water molecules are going to stick to that negative anion. On the positive ion over here, the cation, the negative oxygens are going to bind to that sodium ion. And you can see this happening on your windshield as well. Glass is slightly charged. Does water stick to your windshield? Or does it roll right off? Well, it depends if you got Rain-X on it, right? But if you didn't, you would see that water forms these very distinct channels on your windshield. It's because water is sticking to itself as well as sticking to the glass. This is also why water striders can walk across the top of the water, because the water is sticking to itself, creating what we call surface tension. Water striders are light enough that they don't break that surface tension of the water. That polar nature of water also helps it to dissolve things in water. So if you mix salt or sugar in water, those salt crystals will begin to dissolve as the water molecules start to stick to those different anions and cations. On Earth, water is a liquid at standard temperature and pressure on Earth. Liquid water is the most important form of water for life. We know that there's not any, or not much, we don't know if there's really any life on Mars, but there's not a detectable amount of life on Mars, let's put it that way, because there's no liquid surface water. There might have been a long time ago, but currently there isn't, which is a limiting factor to life. The ability of water to stick to itself and other things is called cohesion. That's when it sticks to itself. Adhesion is when it sticks to other things. So water sticking to itself is going to result in surface tension, which is why this little gecko here can stand on the water and not sink. Adhesion is where you see water moving up very small channels, such as in these celery sticks, up to the top of the plant. That's why this dye has dyed the colors of these celery leaves different colors, because water literally moves up those plant channels, they're called xylem, just through adhesion. One more property of water, ice is less dense than liquid water. What this means is that liquid water is the most dense form of that matter. So it's actually at 4 degrees Celsius that water is the heaviest it can be. It's going to sink right to the bottom. As it gets a little colder, 3 to 1 degrees, it becomes lighter and it floats to the top. So ice forms on the top of liquid water. This is crucial for life as well, because most life formed in a watery environment, in the oceans and in freshwater habitats. If these froze from the bottom, a lot of the life would not have been able to survive, because this surface layer of ice not only insulates the water beneath it, but it also protects these organisms from the surface. I have one more property of water I forgot about, and that's water has a high specific heat. So basically, it takes a lot of energy to warm up or cool down water. This is why we sweat. By getting rid of water, getting water out of our tissues, we cool off faster. We also get dehydrated in the process, but it helps us to cool off. This is also why coastal areas are cooler, because the ocean has a cooling effect. It absorbs a lot of heat out of the air, and in addition, it doesn't change temperature very quickly. A couple more things on chemistry, and then we'll move on to the next topic. Acidity. This is an important thing, especially for environmental science. So an acid, this is a substance that readily gives up hydrogen ions in water. And a hydrogen ion is a cation, meaning it's positive, okay? A base is a substance that readily takes up hydrogen ions or dispels hydroxide ions, OH, that's an anion. So if you put H and OH together, what do you get? Well, there's 2 H's and an O. Oh, H2O, water, right? So we're really just talking about solutions, watery solutions, okay? The pH scale, many of you have probably heard of it, especially if you got a pool, right? You take the little pH test strip and you put it in the water and you determine what the pH of your pool is. You want it to be somewhere around here, right around 7. That's what we call neutral, right? But what do these numbers actually mean? Well, the scale is logarithmic, meaning that each step is 10 times more concentrated. So if you go from 7 to 6, that solution is 10 times more acidic than it was. Notice that acidity, the most acidic you can be is 0, and the least acidic you can be is 14. So let's take a little closer look at what these numbers mean. So acidity, those numbers, 7, 6, 5, whatever it was, is a measure of the concentration of hydrogen ions in solution. Anytime you see these brackets, that's referring to concentration of whatever is inside of them. So this right here means concentration of hydrogen ions. In a watery solution, water is going to split apart. Not all of it, but some of it is. And when that molecule splits apart, you get a hydrogen ion right there, and you get some hydroxide ions. That's what this ion is called, hydroxide. When the concentration of hydrogen ions is greater than the concentration of hydroxide ions, the solution is called acidic. So when you have a concentration of hydrogen ions that is less than the concentration of hydroxide ions, the solution is basic. Once again, these numbers are on a logarithmic scale. So that pH of 7 or pH of 6 is actually this number right here. This is pH 7, 0.000001 moles per liter. So pH is measured in molarity. That's what moles per liter is. And a mole is the number of, so a mole is 6.02 times 10 to the 23rd molecules or atoms if you're dealing with hydrogen here. And we often denote or measure moles in grams. So you would look at the molecular weight. For example, carbon. Carbon's molecular mass or atomic mass is 12.01. So in 12.01 grams of carbon, there are exactly 6.02 times 10 to the 23rd atoms of carbon. Exactly is maybe a strong word, but you get the point. So it's just a measure of concentration. But a pH of 6 is therefore 10 times as concentrated as pH 7. I'm going to challenge you to write down the actual number that pH 6 represents. So pH 7, that's this number. What does pH 6 stand for? The last thing I want to talk about here in chemistry is an application of pH. So carbon dioxide, right? Kind of an important thing to know about in this day and age, especially with climate change. There's more carbon dioxide in the atmosphere, and we're putting more in it every day. But carbon dioxide is a natural part of the environment. In fact, a lot of ocean animals require carbon dioxide to be dissolved in the ocean so that they can build their shells. So when you take carbon dioxide and it dissolves in water, it actually forms an acid called carbonic acid. That carbonic acid will dissociate into constituent ions. One is called the bicarbonate ion, and you'll also get a hydrogen ion right there. So that's going to contribute to the acidity of the ocean. Bicarbonate can further dissociate. It can donate one more hydrogen ion and another ion called a carbonate ion. Carbonate ions are used by mollusks and other shelled organisms in the ocean to build shells of calcium carbonate. Okay? So having carbon dioxide in the ocean is necessary for these shelled animals. But with increased concentrations of carbon dioxide being dissolved in the ocean, it's actually adding more and more and more hydrogen ions to the ocean, increasing the acidity of the ocean water. When you have a decrease in the pH, shelled organisms start to form deformed shells because the acidity literally prevents them from building a stable, structurally sound shell like they did before the ocean was at that level. So this is one really interesting, important application of acidity in chemistry to environmental science, the increase in the acidity of the ocean. Okay, that's where we're going to stop for chemistry, and we'll move on and talk briefly about organic molecules in the next video.